Hello everyone, we are the students from Bangladesh University of Engineering and Technology, and this is our project for VLSI II Laboratory, a 4-bit synchronous decade counter with asynchronous reset and parallel load. So what is a decade counter? A decade counter is basically a counter which counts from 0 to 10 or 10 to 0, and that is active for 10 cycles of clock pulse, and after the end of the count the counter is reset from the start. So this can be either a up counter or a down counter. And here we have designed the decade counter using the Cadence software, and we have used D flip-flop for this particular purpose. So let's have a look at the total number of transistors used in this circuit. So for our design we have used 4 AND gates, 1 NOT gate, 4 XOR gates, 4 D flip-flops, 1 OR gate and 4 muxes. So which amounts to a total number of 240 transistors. And these transistors have been used throughout the circuit. Here we can see the decade counter schematic of our particular circuit. These are 4-bit synchronous decade counter, and we can see the different building blocks of the circuit. We have used 4 flip-flops. These are the 4 flip-flops, 4 muxes, and some logic gates like the XOR gate, AND gate, and so on the top part we have used a particular logic to tap for the asynchronous reset and ensuring that this counter actually stops at 10 or the 10th clock pulse. So if you zoom in a little bit, we can see the different parts clearly. So the main inputs of this circuit is the clock input. This is the clock input, and we also have then enable pin. This enable pin is actually a high. There is 1 for this particular counter. We also have the different inputs for parallel loading, the L0, L1, L2 and L3. These are the loading pins, and these loading pins are actually driven by the pin S. So if this is pin S is high, then this will drive the mux so that the loads can be inserted into the flip-flops. And we also have the outputs. The outputs are the Q0, Q1, Q2 and Q3. So on the lower part we can see the different logic gates like the XOR gate and the AND gate, and these gates are usually used to drive the flip-flops. So what it basically does is that the XOR and AND gate ensure that this circuit functions as a decade counter. If you look at the first XOR gate, we can see that the two different inputs are the first enable pin, which is usually high, that is 1, and it takes an input from the output of the first flip-flop, and this output goes into the mux of the first flip-flop, and into the next AND gate. We can see that it takes an input from the flip-flop output and also the enable pin, and this output goes into the input of the next XOR gate, and this continues on and on until the next XOR gate and up till the 4th XOR gate. So what it basically does is that this XOR gate and AND gate ensures that the value of the flip-flop is toggled at the right time, and whenever the value of S is 0, then the output of the XOR gate is driven into the flip-flop, and thus this functions as a decade counter. And if we go up on the top part, we can see the logic circuit of for the asynchronous reset, and we have an AND gate, OR gate and a NOT gate. The AND gate is used so that the flip-flops are reset on the 10th clock cycle, that is the binary value of 1010. So we're taking the output of the second output and the fourth output. Whenever these values are 1, this will drive the AND gate to be 1, and this goes into the OR gate along with the asynchronous reset. So the asynchronous reset means that the value of the flip-flops will be driven to 0 whenever this reset is 1. And so we have used an OR gate, and since this is an active low reset, we have used a NOT gate, and this total output goes into the reset pins of all our 4 flip-flops. So in this way we can see how the decade counter works, and now we are going to dive a little deeper into how each and every block functions or works. Okay, so now let's have a look into the schematic of the AND gate. So here we can see the schematic of the AND gate. We have used 2 PMOSes and 2 NMOSes. The PMOSes are arranged in parallel and the NMOSes are arranged in series, typical for the AND gate. And we have used the CMOS inverter so that the output is AND instead of NAND. And this particular circuit serves as a 2 input AND gate. So let's have a look into the layout of the circuit. So this is the layout of the circuit. We can see the 2 input. This one is the A and this one is the B, and this one is the output J or Z. And we can see on the top part this is the VDD, and the lower part this is the ground. We can also see 2 different contacts, this one and this one. These contacts are used as body of the particular transistor, and we have connected the different connections by using metal one. This blue one, these blue layers are the metal one, and the green ones are the polysilicon, and we have used different bias to communicate between them. And this particular layer over the PMOS area, this is the N well. This N well serves as a substrate for the PMOS. And now let's have a look into the symbol of the AND gate. So this is the symbol of the AND gate, and in cadence the part name and instance name have been given here, and the upper part is a VDD and the lower part is a ground, and different levels have been placed to show the inputs and the outputs. So now let's have a look into the schematic of an OR gate. So in this circuit, this is a bit similar to the AND gate. Only difference is here is that the PMOS are connected in series and the NMOS are connected in parallel, and we have an CMOS inverter in the output so that the output becomes OR instead of NOR. And this is also a 2 input OR gate, and we can see the different pins for the VD ground, and A and B are the inputs and Z is the output. So let's have a look into the layout of the circuit. So the layout of the OR gate is almost similar to the layout of the AND gate. The only difference is that the PMOS over here is connected in series and the NMOS is connected in parallel. Where we have used a similar N-well layer as a substrate for the PMOS, and we have used different contacts for the to act as body of the PMOS and the NMOS transistors. And here we have the A, B, which is the inputs, and the Z, which is the output. We also have the VDD and the ground. This one is the ground. So the overall structure is pretty much similar to that of an AND gate. So this is the layout of the OR gate. So let's have a look into the symbol of the OR gate. This is the symbol of the OR gate. We can see the different levels. There is A and B. These are the inputs, and that is the output. And we can see also the levels for the VDD and the ground. So here we have the schematic diagram of the multiplexer. That is a 2:1 multiplexer which we have used in our particular circuit. So the 2 inputs are the A and B, and these inputs are driven by the control pin S, and we have used two NMOSes to control the output Z. So whenever the value of S is 0, then the value of A passes through the Z, and if the value of S is 1, then the value of B passes into the output Z. So this is how this particular marks works. Now let's have a look into the layout of this marks. So in this particular marks we have used the metal 1 layers and polysilicon layers, and it's pretty similar to that of an AND or OR layout. This is the N well. The N well has been used as a substrate for the P MOSFETs, and these are the N MOSFETs, and the connections have been given appropriately. So, and now let's have a look into the symbol of the marks. So this is the symbol of the marks. These are the labels, and this is the control pin, and this is the output has been given as set. So let's have a look into the schematic of the D flip-flop that we have used. So this is the schematic of the D flip-flop that we have used. This is a positive edge triggered flip-flop. So if we zoom in a little bit, we can see that the different inputs of this circuit. The circuit is the C, that is the clock of the circuit, and D input of the circuit, and R is the reset pin which has been used, and this is an asynchronous reset pin, and we have the VDD and the ground pins, and the output is Q. Q is the output, and the inverting output is the Q prime. So we have used six 3-input NAND gates for this particular circuit, which is connected in proper way, so that this particular circuit functions on the positive edge of the clock to give the proper output. So let's have a look into the layout of this circuit. So this is the layout of the circuit. So as we can see, the layout is pretty complex. If we zoom in, we can see that the various blocks. There are 6 blocks of the NAND gate which have been connected properly through polysilicon and metal 1 layers, and we have used some vias. The vias has been used in from metal 1 to polysilicon vias, and we can see the different connections connections of AVC, which are the basic inputs, and these have been connected appropriately, and we have also done the DRC and LVS checkup, and those are just fine. And here we have the outputs, the Q and the Q prime, and the inputs are here is the clock input C, the input for D, and the reset pin R, and thus the connection have been given appropriately. So let's have a look into the symbol of this flip-flop. So this is the symbol of the flip-flop. We can see the different labels of the inputs and outputs, the reset pins, the grounds, and the VDDs. So we have already seen the schematic of the final decade counter. So now let us have a look into the layout of this decade counter. So this is the layout of the final decade counter. So from this figure, we can see the various blocks of the layouts of different parts of this counter. The middle blocks are the flip-flops. Then we have the marks, and we also have the XOR gate, AND gate, and these are the XOR and AND gates. And we also have the logic of the upper part, the NOT gate, the OR gate, and the AND gate. So for our purpose, we have used the polysilicons and metal 1. We could have also used the metal 2, but for this particular diagram, we have used only polysilicon and metal 1. So here we can see the connections of internal connections of different types of transistors and output and input pins. So let's have a look from the top. So this is the VDD. We also have the clock, and this is the load pin 1. We also have the control pin S. Then this is the load pin 2, load pin 3, and load pin 4. And this is the output. This is the fourth output, third output, the second output, and the first output. We also have the enable pin, which is in this case is this one, and we have the ground on the bottommost part. So this connection is pretty complex, and it takes a lot of time, but the connection is pretty accurate. And after the performance of the after completing the layout, we can do the LVS and DRC checkup, which we have done. So now let us see the output of this decade counter and see if this works. So for that we have launched our ADL from Cadence, and this is our decade counter, and now we're going to test it. For that we've chosen a transient analysis of 200 microsecond, and now let's see if this works. Okay, so from the graph we can see that our circuit is pretty accurate, because because it starts from 0 0 0, and the count ends at around right around the 10th clock cycle. For this particular purpose we have set our reset pin and the load pin to be 0, so that we can test our circuit. And as we can see that the outputs change only in the positive clock edge of this of the clock. For the same is true for Q2, for Q1, Q2, Q0 and Q3. All of this is changing in the positive clock cycle, and this continues just until the 10th clock cycle. So from this we can understand that our graph is pretty accurate, and this is a functional 4-bit synchronous decade counter. So thank you all for listening, and that is all for our project, the 4-bit synchronous decade counter with asynchronous reset. I hope you liked it. Thank you.